Welcome back. So today we're going to be talking about implementing subduction in the kill chain world generator simulation. So if you watched the last video, you'll know that I am working on a strategy game called Kill Chain. I want to have realistic planets to base the game on, and so we constructed a globe and split it into tectonic plates, and we were just about to start making them moving. And that's what this video is all about. So I have actually managed to create the first of the weekly installments, which I'm rather pleased about. So today we're going to talk about the theory of subduction and why that's the first thing we're looking at. We're going to look at some improvements I've made to the visualizations. We're going to talk about how far I got with implementing this, which is not complete but significant progress. And then we're going to talk about what I'm hoping to achieve next to complete this part of the project. So, the theory of subduction. Once a section of lithosphere gets old enough, it will start to sink into the asthenosphere below it. And this is a process known as subduction. It can also be triggered by collision with another plate, which we will talk about later. If you look at this diagram, as it starts to sink here, it drags the rest of the plate along with it, and this is applying a moving force to the plate, and this is currently accepted as the most powerful force driving plate motion, so it seems like a good place to start in adding plate movement to our simulation. So there are some details we need to think about, and I'm going to talk slightly more detail than the model needs. This is so that we know which bits are important, which details matter and which don't, and which features we need to capture. So why is it old crust that subducts? And that's fairly simple. Basically, as oceanic lithosphere ages, it cools down, it contracts, it becomes denser, and eventually it becomes denser than the asthenosphere beneath it. The asthenosphere is solid on human timescale. So if you drilled down to the asthenosphere and stamped on it, you'd burn your foot off. But if you had a fireproof foot, it would feel like stamping on rock. To you or me, we would not know any difference to normal rock. But on geological timescales, it's hot enough and soft enough that it can flow. And so if the crust above it, the lithosphere above it, crust and lithosphere are different, I will keep mixing them up. If the lithosphere above it is denser, it will, over geological timescales, start to sink into it. But there were some things that were confusing me about this. And the main one was, why doesn't it subduct immediately? And by immediately I mean as soon as the lithosphere is denser than the asthenosphere. Because lithosphere becomes negatively buoyant at about 30 million years. But pure age-based subduction seems to occur around 200 to 300 million years. So why is that? Something else must be holding it up. It turns out what's holding it up is the strength of the lithosphere itself. Now, this seems quite counterintuitive. The lithosphere is quite thin compared to its size, and it feels intuitively in my head like a piece of paper or a piece of card. It doesn't feel like it would have that much strength. And when this clicked for me was when I realised the plate is not a flat plate, it's actually curved because it's sitting on the surface of the Earth. So if you imagine these were two pieces of paper, this one, if you wanted to put a line across here and bend along that line, that would be quite easy. If you tried to do the same thing here, where the plate is already curved in this direction, or the paper rather is already curved in this direction, it's very much harder to bend a curved piece of paper than a flat. And this is to do with geometry. You would have to compress parts of the paper and stretch other parts to bend it when it's curved. You don't when it's flat. So these bending forces support the crust for a very, very long time, even when it's negatively buoyant. They also impart a curved shape as it descends. So if you think about it, once the negative buoyancy builds up enough that it can start to bend it, it will only be able to bend it so far, and so you will have like a constant radius of curvature. Or I mean, it can change with various factors, but you will have a radius of curvature rather than a sharp edge, which is what you see in all the textbook diagrams. And if you ever see kind of seismographic reconstructions of a subducting plate, it is curved, and that's why. Okay, so then I had another question. We know that old crust sinks faster than young crust. And I was thinking, why? Because the intuitive answer, and what I've often seen presented, is that young crust is hotter, so it's more buoyant and it doesn't sink as quickly. But that doesn't make sense, because the amount of force you need to overcome the bending force is the same, regardless of how young or old the crust is, how warm or cold it is. I mean, the heat will have some effect on the ductility, but not enough to really factor in. And so I spent quite a bit of time this week studying this and reading up on this, and what it seems to be is that whilst the negative buoyancy is the initiator of subduction, and it is a major factor all through subduction, it isn't the only factor. And once a plate gets down to about 100 kilometers of depth, it will undergo a process due to the pressure where the basalt starts to convert to a different type of rock called eclogite, which is much denser. And so you get densification just from being at depth, which is not related to the buoyancy. No, it is. Which is not a cooling phenomena. It's a chemical process. Now, this process is age dependent, and it happens more slowly in young crust, which means young crust densifies more slowly and hence subducts more slowly. And some of the sources I found suggested that this is due to the temperature, but others suggested temperature has the opposite effect, so I'm not quite sure, but for our purposes all we need to know is that this densification is slower in younger crust, so it subducts more slowly. This also is why colliding plates can cause subduction. So if you see this diagram here where a plate has hit another one and this plate is slightly more dense and it's been forced underneath, it doesn't actually have negative buoyancy yet, so it won't sink, but it is under the conditions that form eclogite to form, which means it will start to densify, and eventually it will become denser than the asthenosphere through that process, and it will sink through that process. So that's the theory. Let's move on to some implementation. So, improvements to visualization. So we need to visualize certain properties that we can't do on the globe mesh we were using last time. So in particular, we need to look at places where plates overlap. We need to look at the movement of points. So the points on the globe mesh are fixed and we were just assigning different IDs and they would jump. So the plates on them would move in discrete jumps. The plates themselves hold points as continuous values, and we need to be able to visualize them moving. And finally, the actual deformation as the points start to sink, we need to be able to see that. So I've added a new render mode that renders a plate rather than the whole globe, and it draws all the points in the plate where they really are. Now, plate isn't actually a mesh. I did initially hope I could just carve out a section of the globe mesh for this. However, if you remember the last video, there were certain holes in meshes. This means the indices are all messed up, and you can't do that. You could remesh the plate, but that would be a slow process, also a complicated piece of code. They're probably libraries, but all in all it seemed more faff than it was worth. So instead what I'm doing is drawing a pyramidal marker at each mesh point. And finally, I've centered the camera on the plate in this mode and not the globe. So I will show you this mode. So here we're looking at the globe mesh where we have the new mode. Here we have the plate mode. As you can see, each vertex is now represented by a little pyramid. You can zoom in and out and rotate. Rotation is particularly important for looking edge on, where you need to be able to see folds in the plates, which are going to be very important in a minute. You can also cycle up and down through the plates, pick whichever plate you want to focus on. Lets you look through all of them. Obviously you don't just want to have an arbitrary one. Let's talk about where we've got to with the subduction implementation. So we've got three objectives here. The first is assign an initial age to each point in the globe. This is fairly straightforward. We're going to assign an age, maximum age to each plate, and then The points are just assigned ages on a gradient from 0 to that maximum age, moving spatially in one direction across the plate. Very, very straightforward. The major part of the project is to get the points to sync. So we're going to go with a linear model here. I was talking about the bending forces causing this kind of curved roll-off. We're not doing any of that. We are considering a plate to either be flat or to be subducting, and the subducting bit will have some wiggle, but it will be basically linear. And this is going to be good enough for what we need. It's probably good enough for a lot of geological simulations, to be honest, depending on what you're trying to achieve, but from what I've read, that is quite a common approach, and it's what we're going to do. So each point is going to be assigned a sync rate based on the temperature at the start of subduction, and so the hotter the point was when it started to subduct, the slower subduction will occur, as we were just talking about in the theory section. And then the sync rate is going to be the time since the subduction started times the sync rate, and that will, assuming these points were created, have a nice linear gradient of age, which we just talked about. You will get this nice linear dip here. And then finally I want to increase the point age over time so that you will see these points sink further and this trench move backwards this way. So here we have the globe mesh with some of the subduction implementation. So first off, you can see we have the temperature map. This is actually age, but age correlates to temperature directly, so it's both. And if we go into the plate mode, so we can see a plate here with quite a fold point in it. So you see this is on the globe, and that is subducting. You can tell because the blue is the older end. This does have some, but only a few at the very end, so it's very hard to see. This one and a few others, there is a fold, but it's somewhere in the hot zone where it's quite shallow. And here you can see one here. And then finally I'm going to look for one in the cooler end to show you that it gets sharper, a steeper angle of subduction when subduction starts in the cooler crust. So this is quite a shallow one. Here we are. This one is quite steep, or at least certainly steeper. Now obviously this is a bit of a diminishing returns thing because the steepness is a function of the square root of the temperature. But yes, as you can see, it's quite a sharp angle here. Some of the ones here were less sharp, and the ones up here were so shallow you could hardly see them. Now, if we look at the next video, we're looking at a crust sinking with age. So if we find a plate that demonstrates this well, you can see it's quite warm over here, quite cold here, like as previously, but now this is cooling down. The point where the plate subducts is advancing, so the trench is moving, and it looks like the subduction just stopped and the plate started moving. That's actually the camera just being attached to a point that suddenly started subducting. So you see the subduction moves all the way along the plate. Eventually the plate itself will be pulled in this direction, so the point of the trench will be relatively static, but the plate will be consumed as it subducts, which is what we want. And if we look, this took about 246 million years, which is what you would expect with a plate that had crust that was from 0 to 246 million years old. And there we are. Moving on. What's next? Because that's as far as we got. So 3 things that I'm hoping to achieve this week. I don't know if I'll get through them all. I'm certainly hoping to get through the first 2. First one is to remove points once they reach 500 kilometers of depth. Now, plate continues to exist when it gets down here, but it loses some of its mechanical strength due to heat. It doesn't have a major impact anymore on subduction, so we're going to just delete it from the simulation for the sake of computational efficiency. Should be fairly trivial to achieve. The next thing is to actually start to use this to now pull the plates around, and I've already started some research on this, because the slightly non-trivial part of this is what direction does a point pull the plate in, because a point doesn't actually... The plates aren't a surface, they're just a collection of points. So how do you know which direction? Now you could try and find the neighbours, and we do have some neighbour information. Probably isn't accurate enough for this, but if you could probably find the neighbours, find the slope, and do it that way. That's going to be a bit noisy, and like I say, due to the holes that we looked at last week and that caused problems that we talked about earlier in the video, that's a bit of a problem. It's not a trivial thing to achieve. So then I was thinking, well, could I do it more simply by just taking the vector here, looking at this vector from the plate centre, this isn't quite the centre of this diagram, but we'll assume it is, to the subducting point. Now the problem here is if you imagine projecting this up to the plate, it would be here somewhere, yeah, about here, and then this vector here, it has a component in this direction which we want, but it also has a component up that way which we very much don't want. This would make this plate slide that way. Additionally, well, it wouldn't because this is even, but you can imagine a plate that had a funny shape where these were cut off and these two weren't subducting and these were, and that would apply a kind of sliding force in the wrong direction. We don't want that. The other problem here is, since they're all pulling towards the centre, there will be no rotation, there will be no torque to spin the plate around its axis. And that is something that you do actually see in the real world. If you look at simulations of plates moving from Pangea breaking up, they all show plates rotating somewhat. So then I realised we can find where the trench is by finding all subducting points that have neighbours that are non-subducting. Now again, this will be a little noisy, but it'll be good enough because that noise will be very small and the vectors we're finding will be quite large. And then you will find the nearest point to the subducting point and take the direction between the trench and the subducting point. So now if you look at this, if we project this back up and we come across here, this direction is purely forwards, which is exactly what we want. We also get this nice lever arm here so we can calculate some torques and do some rotation. And then finally, as this crust sinks at a certain point, somewhere here-ish probably, it will become warm enough that the water will leave, will evaporate out. This will cause melting in the magma above, which will cause volcanism, and you will start to get arc volcanism and island building, mountain building if you were. If you had continental plate above you, if you have oceanic plate, you'll just get some island arcs, which yes, I would very much like to start to incorporate into the simulation. We'll see if we get there. So as ever, thank you for listening. I'm quite pleased I actually managed to make enough progress to do a weekly update. I'm hoping I will again next week, but I'm back at work, so we'll have to see. As ever, any suggestions, feedback, thoughts for improvements, very much welcome. Thank you very much. I will see you next week.